So hello, I will start recording you already recorded, right? Okay.
I did, yes.
Thank you, Sio. So good afternoon, everyone. Welcome. So this afternoon we will have the first of the three lectures of Martina Gerbino from the INFN, Sessione di Ferrara. It's a pleasure to have her as a speaker and as a lecturer. And then she will tell us the first of these three lectures about the Big Bang cosmological model, theory, and observations. Thank you very much, Martina. Thank you.
Thank you, Olga, and thanks all the organizers of this school. And it's a pity that we cannot be there in person, but we'll try to do the best to make this more interactive, as possible. And in this regard, please feel free to ask any questions that you can have also during the presentation and during the office hours in Gathertown. I will be there after the lectures if anybody wants to ask further questions or have comments and discussions. So we have 3 lectures for 1.5 hours, and I'll try to cover these topics listed here. And in particular, during the first lecture, we'll try to go through the background expansion of the universe and then move to understand how we can describe the perturbed universe, since we know and we observe perturbations, actually large-scale structures in the universe. We'd like to know how they were seeded and how they evolved to form the universe that we observe today. And finally, I hope that we will have time to go quickly through how the initial seeds of these perturbations were put in the universe, and what is the current paradigm that we consider the most suited to describe how the universe began, basically. And we will see in the next lectures the other topics, but basically during the second lecture we will try to cover all the remaining theoretical aspects of these lectures, mostly how the perturbations in the matter field evolved to form the large-scale structure of the universe, and how CMB fluctuations evolved to form the current picture of the CMB sky, the cosmic microwave background sky that we observe today. And finally, in lecture 3, we will go through some observational evidences of the standard cosmological model and how we can use cosmological data to constrain not only properties of the universe, but some basic properties of fundamental physics. And finally, what are the prospects with the next generation of cosmological surveys? But let's get started with the first lecture. Here there is a rather incomplete list of some references that might be useful for those of you who are approaching the subject now, but also for those of you who are already expert and want to know more and understand more about the basics of cosmology. I'd like to start with this first sentence that I took from the book by Kolben Turner. This is a picture of how cosmology was mostly 30 years ago, and 30 years ago cosmology was already a very robust theoretical area of research, but the quantity and the quality of data was not comparable with what we have today. And so there was already the idea that cosmology was going to become a more robust area of research, but the picture today is completely different from 30 years ago. We know today that the standard model of cosmology, what we call the standard model of cosmology, is a well-established description of the evolution of the universe. And it's rooted in two main areas, and one of that is the general relativity that describes the metric of the universe and how the interaction between the metric and the content of the universe evolves. And it's also based on the standard model of particle physics that is used to extrapolate some important properties of the universe at early times, where the conditions of the universe were completely different from whatever we can reproduce in the lab today. But nevertheless, they led to very precise predictions that we can and that we could subsequently compare against a good quality of data and therefore validate our understanding of the universe from a theoretical point of view. This picture is complemented with a theory for or a paradigm for the generation of the primordial seeds that later evolved into the observed universe, which is the inflationary paradigm. A more detailed description of how the standard model of cosmology is today is provided in this slide. I will not read through it, but I'd like to leave it here for further references. I think that these slides will be shared with the participants. So I'd like, in general, I kept these slides very wordy so that you can have a reference for further studies, or if you want to look at the slides in the next days, you will have something more wordy, more concrete to read through. From current observations, we know that the universe is expanding, and we also know that the universe is homogeneous and isotropic at large scales. So if we consider large enough volume of the universe, we observe an overall extremely high level of homogeneity and isotropy. And the best metric to describe this kind of picture of the universe is the Friedman-Robertson-Walker metric that is written here in these slides, where basically the expansion of the universe is encoded into this term here, which is the scale factor. And since the universe is homogeneous and isotropic, it only depends on time. We can also define, written in this way, the scale factor takes the dimension of a length, but we can define a dimensionless scale factor, A, and rewrite the metric in this way as written in the second line, where we also introduced the conformal time d eta, which is the proper time dt divided by the dimensionless scale factor. This way to rewrite the metric is very convenient because it shows that the Friedman-Robertson-Walker metric locally appears as the Minkowski metric. So the Friedman-Robertson-Walker metric is affine to the Minkowski metric, the metric of a flat space-time. From this metric and from the geodesic equation, we can start deriving some information about the kinematics of the universe, and in particular, if we take the 0,0 component of the geodesic equation, and after some algebra that you can easily follow in any of the textbooks that I listed in the references, we can derive this important relation between the momentum of a given particle and the scale factor. This one is telling us that the momentum scales as the inverse of the scale factor. This is both for massless and massive particles. And for massless particles, this also means that the energy of the particle scales as the inverse of the scale factor. Why is this important? This is important because it allows us to relate the scale factor with another important quantity in cosmology, which is the redshift. Basically, since we can connect the redshift, or if you are more familiar with the classical Doppler shift, we can relate this quantity with the wavelength or with the frequency of the radiation, and therefore, since for a photon, for a massless particle, the frequency is related to the energy of the particle. From this very same relation, we can derive the expression that links together the redshift to the scale factor, and basically redshift and scale factor are the inverse of each other. The redshift is an important quantity because it is one of the pillars, observational pillars of the standard cosmological model. It was realized back in the days, almost 100 years ago, that the objects were receding from each other, and that the light emitted from distant object was redshifted the more the object was farther from us, and that put the basis for considering our universe as an expanding universe in contrast with a static universe. So it has an important historical origin, but at the same time is also an important ingredient of the description of the standard cosmological model. We have said that another important basis of the standard cosmological model is the general relativity. And the description of how the content of the universe influences the metric is given by the Einstein equations that are represented here in this slide. In a homogeneous and anisotropic universe, the content of the universe can be described through the stress energy tensor of a perfect fluid. The stress energy tensor of a perfect fluid takes a very simple expression. It is a diagonal tensor with the two components that are given by the total energy density of the component and the pressure of the component, or the isotropic stress of the component. From the Einstein equations, we can derive some important considerations about the dynamics of the universe. So far we have discussed about the kinematics, and we have derived the important relation between the momentum and the scale factor. And now we will focus instead on the dynamics of the expanding universe. In particular, from the 0-0 component of the Einstein equations, we can derive the first Friedmann equation that describes the expansion rate of the universe. The ratio between the time derivative of the scale factor and the scale factor itself is called the Hubble parameter, not to be mistaken with the Hubble constant. Basically, they are related, but while the Hubble constant is the value of the Hubble parameter today, the Hubble parameter is a function of time. And is related to the energy density of the universe and to the curvature parameter that is written here, rescaled to take into account the fact that we have introduced the dimensional scale factor. I haven't said that before, so let me just go quickly back to the expression of the metric. Yeah, here. K is the curvature parameter and describes the geometry of the three-dimensional part of the metric. And in particular, for k equal to 0, we have a flat geometry, whereas for k equal to +1, we have a closed geometry, and with k equal to -1, we have instead an open geometry. And so the same factor is the one that we retrieve here in the Friedmann equation. The Friedmann equation that describes the expansion rate of the universe can be coupled to fully describe the dynamics of the universe to the fluid equation, which is the second equation that appears in this slide. The fluid equation can be derived from the conservation of the stress energy tensor, and is basically relating the energy density of the universe to the pressure of the components. And this relation is further explicit in the equation of state, which we'll see in a while will take a very simple form if we consider different components. But if we couple together the Friedmann equation, the fluid equation, and the equation of state, we have all we need to describe the dynamics of the universe. Let me just add that from the II component of the Einstein equation, we can also derive the second Friedmann equation that is written here, but this equation is not independent from the others. So basically, we can choose a combination of these equations, and only three, if we consider the equation of state, are independent out of the four that are written here. As I said before, we can derive some notable forms of the equation of state, and basically the relation between the pressure and the energy density can be written in terms of a proportionality constant W that takes a different value if we consider the different components that we can find in the universe. For example, for a matter component, which is a component of non-relativistic particles, W is equal to 0. Whereas for a radiation component, or a component that is filled with ultra-relativistic particles, W is equal to 1/3. And finally, for a rather mysterious cosmological constant, or dark energy, W is equal to -1. In general, from the fluid equation, if we use this expression for the equation of state, so for a constant W, we can derive the evolution of the energy density as a function of the scale factor in this way. That can be, and this can be obtained simply by solving the fluid equation and rewriting the pressure in terms of the equation of state. We can obtain, as I said, the evolution of the energy density of the universe as a function of the scale factor. And we can see by plugging here the different values of W that we obtain for the different components, that we can identify very specific epochs during the evolution of the universe where each of these components was the dominant one during that specific epoch. As reported in this plot on the right, you can see on the x-axis the scale factor that is growing from left to right, and on the y-axis I reported the evolution of the energy density in arbitrary units for the different components. Radiation in purple, matter in green, and cosmological constant in blue. And so we can see that at very early times, so for very small values of the scale factor, radiation was the dominant component until more or less here, where the matter component takes over both radiation and the cosmological constant until very late times, when instead is the cosmological constant to become the dominant component in the universe, superseding both radiation and matter. Using the relations that we have found so far, and rewriting the Friedmann equation in terms of the different components instead of a generic energy density, we can see that the Friedmann equation takes now this form that can be further simplified if we recast all the terms that are independent from the energy densities, introducing the critical density rho c, and defining the density parameter omega I as the ratio between the energy density in each of the component and the critical density, and the omega and the density parameter also for curvature in this way. And with all these different parameters, we can rewrite the Friedmann equation in a kind of simplified way, also in terms of the redshift instead of the scale factor, where again it's evident how depending on which epoch we are considering, there is one component who is dominating against the other. When we consider the epoch where a single component dominates and curvature is negligible, we can solve the Friedman equation to find what is the evolution of the scale factor or the redshift as a function of the time, and we obtain this equation here that is valid as long as we consider W different from -1. So in the case of radiation domination, we get that the scale factor is evolving as the square root of the time, whereas in the case of matter domination, where we substitute W to 0, we get that the scale factor is evolving as T to the 2/3. Let me conclude this first introductory section by walking you through the different distances that we can define in cosmology, and why I'm discussing about distances instead of just one single distance will be clear in 1 second. First of all, we can define the proper distance between two objects, which is basically the integral of the radial component of the metric when we fix both the time and the angular coordinates. So this is the proper time, and note that all the distances that I will discuss here are physical distances. In order to find the comoving distances, you have to divide all these physical distances for the scale factor. The proper distance is important, but unfortunately is not the distance that we can observe. It's not the distance that we have access to with observations, because it will require to have synchronized clocks throughout the universe, and you understand that this is unfortunately not possible. Therefore, we have to introduce some phenomenological distances, which are the angular diameter distance and the luminosity distance, that are written here in terms of the metric and redshift, or the scale factor. Their explicit form is not really important. What I'd like you to understand is the meaning of these distances. They are related to different classes of objects that we can observe in cosmology, that we can use to constrain and to understand the background evolution of the universe. I'm seeing that there are some questions on the chat. What is K here? K is the same parameter that that I have defined before, and it's simply distinguishing between the different geometries of the three-dimensional space of the for the three-dimensional spatial part of the metric. So again, k equal to 0 is for flat universe, k equal to +1 for closed universe, and k -1 for open universes.
Martina, they can also raise their hand if they want to ask something. Okay, so
okay, yeah, I just noted it because it popped it on the top right of the screen, so I saw that somebody has written something in the chat.
There is only one question. Yes.
Okay, so we were saying that the angular diameter distance and the luminosity distance are important because they are related to two different classes of objects that we can use to constrain the background evolution of the universe. The luminosity distance is related to the so-called standard candles, which are objects of known luminosity. And these objects are important because we know their intrinsic luminosity, and by comparing their apparent luminosity against their true luminosity, we can infer their distance to us. And by comparing this distance with the expression that we can write in terms of the luminosity distance, we can constrain the parameters, basically the density parameters or the energy density of the different components that drive the background evolution of the universe. The same is true for the angular diameter distance, but in this case, the angular diameter distance is not used with standard candles, but with so-called standard rulers. The standard rulers are objects or distances of a known intrinsic length. We will see some examples of them, especially in tomorrow's lectures. And in this case, what we measure is the distance between us and this object or this intrinsic length that subtends a given angle given their distance. Basically, this is a definition of the parallax, but in the expanding universe. And again, by comparing their angular size that we see projected on the sky with their intrinsic size that we know from either from first principles or because we understand the physics that governs these objects, we can infer their distance to us, and by comparing this distance against the angular diameter distance that we can write in terms of the energy densities of the different components, we can constrain the energy density of the different components or a combination of them. Basically, both the angular diameter distance and the luminosity distances are very important to constrain the geometry of the expanding universe, as we will see, especially in the third lecture. So this concludes the first introductory part to the basics of kinematics and dynamics of the universe, and now we will start second chapter by discussing the thermodynamics of the expanding universe. And before I move to that, I'd like to ask if there are any questions so far, or if there is anything unclear. Okay.
I don't see any raised hands, so you can go out.
Okay. Okay, and feel free to ask anything after the lecture if you want. So let's start with the thermodynamics and basically with the description of how these different components of the universe interact with each other. So far we have seen how these components drive the expansion of the universe, and now we would like to focus more on how they interact with each other. Let's remember that the early universe had very peculiar conditions. We were in a very dense and also very hot environment. And in this environment, the rapid interactions between the different components were very efficient in keeping all the species in both in chemical and in thermal equilibrium. In these conditions, it is possible to express the energy density, the number density, and the pressure of the species by using the equilibrium distribution for the different species, which is basically in the case of ultra-relativistic species, the Bose-Einstein for bosons and the Fermi-Dirac for fermions. And given their distribution function, we can write down very easily their number density, their energy density, and their pressure as integrals over the momentum distribution. We see here that the distribution function is a function of both the temperature, the energy, and also the chemical potential. This mu term here is the chemical potential of the species. It's written there for writing down the most generic expression of the distribution function that we can think of in a homogeneous and isotropic universe. But insofar, I will assume that the chemical potential is vanishing unless otherwise stated, and unless it is important not to be vanishing. Given the expression for number density, energy density, and pressure, we can work out their explicit expressions for some limiting case. For example, in the ultra-relativistic limit, where the temperature of the universe was much larger than the mass of these of the particles, and also in case of non-vanishing chemical potential, much larger than the chemical potential itself, the number density takes this very simple form. Basically, the number density scales as the cube of the temperature, and the energy density instead scales as the fourth power of the temperature. The two numbers here in square bracket, 1 and 3 over 4, or 1 and 7 over 8, are for the two different statistics. So 1 is for bosons, and the number on the bottom is instead for the Fermi-Dirac statistics. Given the number density and the energy density, it's easy to find what is the average momentum for a given species, which is more or less equal to the average energy of a given species, and we can see that it scales as the temperature of the universe with a different prefactor depending again on the statistics. In the opposite regime, so for non-relativistic particles, when the temperature of the universe drops much below the mass of the particle, of course, the number density takes a different expression. The energy density is related simply to the mass of the particle times the number density, and the pressure of the species is much smaller than the energy density. And here we recover the equation of state of a massless particle, where we saw that rho is where we saw that W was almost equal to 0 for a massive particle. In the early universe, we have also seen that radiation was the dominant component, and therefore the universe was radiation dominated. The energy density at a given temperature is in this epoch is dominated by the species which is still ultra-relativistic. So we can write down the total energy density of the universe during radiation domination in this form, where the sum runs over all the ultra-relativistic particles, and the sum has been split into the bosonic species and the fermionic species to take into account the fact that we have a different prefactor, as we've seen for the two species. The reason why I introduced this ratio between the temperature of a given species and the temperature of the universe is very important. Basically, it is possible that at some point a given species decouple from the rest of the other components that are still in equilibrium with each other, thanks to the very efficient interactions between the different components. We will see in a while when this happens, the evolution of the temperature for the decoupled species is different from the evolution of the temperature for the still coupled species. So it might be possible that while we'll still have different relativistic components that contribute to the energy density of the universe at a given time, the evolution of the temperatures for these different components is different. And we have to take into account this to write down the full and complete expression of the total energy density in radiation in ultra-relativistic species. We will see in the lectures about neutrino cosmology how important this distinction is. But for the moment, just remember that it is important to distinguish between coupled and decoupled species. This sum here, which is the sum over the different bosonic and fermionic components, weighted for their internal degrees of freedom, can be recasted in terms of this G star, which is the total number of relativistic degrees of freedom. And in terms of G star and the total energy density in radiation, we can write down this expression for the Friedmann equation as a function of the temperature instead of the scale factor. This is nothing but a rewriting of the Friedmann equation that we have seen a few slides before in terms of the temperature instead of the scale factor. And M Planck here is the Planck mass, and is basically linked to the gravitational constant G that we saw already in the Friedmann equation. Another very useful quantity to define, to describe the thermodynamics of the expanding universe is the entropy density, little s. And again, by using the expression that we've seen before of the energy density and pressure integrated over the momentum distribution, it's easy to see that the entropy density scales as the cube of the temperature for ultra-relativistic species. Similarly to what we have done for the energy density, we can write down the expression for the total entropy density, dominated again by ultra-relativistic species. And again, here we have the distinction between fermion and bosons. And again, we have the distinctions between the temperature of the individual components compared against the temperature of the universe. Similarly, we can recast all this sum here in terms of this term G star S. And the total entropy density is simply written in terms of G star S in this way. As long as by comparing this expression with the expression that we have seen before of the energy density in radiation, it's easy to understand that as long as all the particles are coupled to each other, and therefore the ratio between the individual temperature over the temperature of the universe is equal to 1, G star is identical to G star S. There is an important difference when we start to have some components that decouple from the rest of the plasma, and therefore their temperature is different or scales differently with respect to the temperature of the coupled particles. And at that point, G star and G star S are not interchangeable anymore. And we have to be careful in distinguishing between the two when we are considering the energy density in radiation or the entropy density. Again, this will be very clear and very important when you will follow the lecture on neutrino cosmology. From the continuity equation, we can derive also an equation for the conservation of entropy. And by rewriting the continuity equation in terms of the entropy density, we can find that the total density in the universe is conserved. And if the total entropy is a conserved quantity, this means that the entropy density scales as the inverse of the scale factor to the 3. Since S scales as a to the minus 3, but we have also seen that small s basically is given by G star S time T cube, it's easy to understand how the temperature of the universe evolves in terms of the scale factor. And we find this relation here. So T is proportional to the inverse of the scale factor times the inverse of G star S to the minus 1/3. This is very important because this is the scaling of the temperature of coupled species. We will see in a while that the evolution of the temperature of a decoupled species is different from this expression. And And it will be a demonstration of what I said before, that it is important to distinguish between the two temperatures when we write down the expression of the total energy density and the total entropy density. This plot here is a summary of the evolution of the degrees of freedom in radiation and the degrees of freedom in entropy. We've seen on the x-axis the temperature of the universe that is decreasing from left to right, and on the y-axis we have both G star for the energy density and G star S for the entropy density. The evolution of both these quantities is very similar. Before looking into the details of this picture, let's just see that the evolution of these two quantities, G star and G star S, is very similar to each other until this epoch here, which is very close to the epoch of electron-positron annihilation, where we start to see a sizable difference between G star and G star S. You will have more details during the neutrino cosmology lectures, but let me just anticipate here that this sizable difference is due to the fact that more or less at the time of electron-positron annihilation, actually slightly before, neutrinos decouple from the rest of the plasma while they are still relativistic. Therefore, they still contribute to both the energy density at that time and to the entropy density, but with a different scaling of their temperature as decoupled species with respect to the scaling of the temperature of the still coupled species. Now let's look a little bit at the details of this plot. We start from the very early universe when the temperature was very high and both G star and G star S were very high, as they took into account the contribution of all the particles of the standard model of particle physics that were still relativistic at that time. As the universe expands and cools down, of course, the temperature decreases and it falls below the mass of some of these particles of the standard model. And as soon as this happens, you see drops in both the G star and G star S. For example, here we have top annihilation, and then we have W, zeta 0, the Higgs, the bottom, and here we arrive to the charm and tau, where we also observe a sudden drop of G star and G star S. And this is due to the QCD phase transition. Basically, we don't have free quarks anymore at that time, and this induces a very dramatic drop in the value of both G star and G star S. And the decrease of both quantities continues as the universe continues to cool down until we arrive to the time of electron-positron annihilation and neutrino decoupling, when we see this different behavior of G star and G star S because of the neutrino decoupling. So this is a very simplified picture of the thermal history of the universe. The important ingredient that we have to introduce now in order to understand how the interaction between the different components drive the thermal history is the understanding of when a given species decouple from the rest of the particles. We have said a few slides ago that the conditions in the early universe were so hot and dense that the interactions between the different components were very efficient at keeping the components at equilibrium. So in order to understand when a given species decoupled from the rest of the plasma, a good rule of thumb is to compare the interaction rate of a given species with the expansion rate of the universe. As long as the interaction rate is much larger than the expansion rate, then we can consider that the interactions are efficient at keeping that species at equilibrium. When this condition is not valid anymore, so when expansion rate starts to dominate over the interaction rate, then interactions are not efficient anymore and the species decoupled from the rest of the particles. This is very easy to understand if we think of the effect of the expansion of the universe. Basically, as the universe expands, the encounters between the different particles becomes much less probable, and therefore the interaction between the different components are not efficient anymore. There are no enough efficiently interactions to keep the particles in equilibrium with the rest of the components. Depending on the mass of the particle, a given species can decouple from the rest of the plasma when the species is still fully relativistic, completely non-relativistic, or mildly non-relativistic. In order to fully describe the decoupling of a given species, the correct way to go is to write down the Boltzmann equation for the evolution of that species. We will see in a while that this is important, especially in some cases. However, we can derive some important results by considering the two limiting regimes, namely the ultra-relativistic and fully non-relativistic cases, because in these cases we can simplify the description and obtain some important results from very simple considerations. So let's start from a fully relativistic particle. Before going to the details, let me just tell you that from this expression here, we can understand that the distribution function of a given species remains self-similar during the evolution of the universe. This is because the distribution function, you can think of this in very simple terms, because the distribution function is basically given by D3 number density, D3 momentum. And the number density is scaling as the a to the minus 3. Whereas we have seen that the momentum of a particle is scaling as the inverse of the scale factor, and therefore D3P is scaling as a to the minus 3, and therefore the two terms cancel with each other, and this tells us that the distribution function remains self-similar throughout the evolution of the universe. When a massless particle decouples from the rest of the plasma, this particle keeps its Fermi-Dirac distribution, but with a temperature that is scaling as the inverse of the scale factor. This can be seen very easily by equating the distribution function right before and right after the decoupling redshift or the decoupling scale factor, as you can see here in this line. And if we interpret, if we write down the decoupling momentum as a function of the scale factor, and then we interpret this scaling by the scale factor as applied to the temperature of decoupling instead of the momentum, then we can see that the Fermi-Dirac distribution is maintained, but with the temperature of the Fermi-Dirac distribution scaling as the inverse of the scale factor. This is to be compared against the evolution of the temperature of decoupled particles, which instead are scaling not as the inverse of the scale factor, but as the inverse of the scale factor times this term here that depends on G star S. And again, this will be very important when you will approach the decoupling of cosmic neutrinos in the next lectures. Now let's consider the case of a massive species. Again, the distribution function remains self-similar. And again, this can be used to rewrite the distribution function right after decoupling in terms of the rescaled temperature of the particle, that now, since we are assuming that the particle is fully non-relativistic, will not rescale as the inverse of the scale factor, but instead it will rescale as the inverse of the scale factor to the second. So the difference between the two situations, decoupling of a fully relativistic species and fully non-relativistic, is simply given by the different rescaling of the temperature of the species after decoupling. And again, this has to be compared against the evolution of the temperature of still coupled species. Note that when we rewrite the distribution function of a non-relativistic species after decoupling, this is still the distribution function of a non-relativistic species, so with the typical Boltzmann term, but we also have a non-vanishing chemical potential, even if we started from a vanishing chemical potential. This chemical potential is an effective chemical potential, is not related to any interaction of the particle, since by definition the particle is decoupled from the rest of the plasma. It's simply there because it has to maintain the form of the distribution function. So this is another important effect of decoupling of massive species when they are fully non-relativistic. Now we have everything in place to provide a slightly more extended description of the thermal history of the universe. This is a very known picture that you can find both in the Colbert-Turner book, but also at Fermilab. So we start from the very early universe here on this slide of the picture, where the universe was very dense and hot, and as the universe expands and cools, we encounter different symmetry breaking epoch and different epochs at which different particles become non-relativistic, decoupled from the rest of the plasma, annihilate, and therefore contribute to the decrease of the energy density in radiation, until we arrive to the time of neutrino decoupling. That is very important for your next lectures, but is also very important for the thermal history of the universe. And more or less at the same time, we have the conditions for Big Bang nucleosynthesis to happen. We will not cover Big Bang nucleosynthesis during these lectures, but it is an important epoch throughout the evolution of the universe, because it's the epoch when the abundance of light elements was set, and it's also one of the most important prediction of the standard Big Bang model, that has been proved by observations, astrophysical observations of light element abundances. After these important epochs, we arrive to the transition between radiation and matter domination, more or less at this time here. And right after, we have the conditions for the final decoupling between radiation and matter. And at this time, the cosmic microwave background, which is the leftover radiation of the Big Bang, decoupled from matter, start to evolve freely in the universe, and the universe is said to become transparent. Until we arrive to the current epoch, when we can observe the temperature, we can measure the temperature, the average temperature of the cosmic microwave background to be around 2.7 Kelvin, which is a very, very low temperature if you compare it against the initial conditions where we started our journey here to describe the thermal history of the universe. Before we move on to describe the Boltzmann equations, I'd like to know if we have comments or questions, or if there is anything unclear so far. Okay, I assume not for...
You are an excellent lecturer, Martina, so everything is super clear.
Or probably a very bad lecturer and nobody is understanding anything.
No,
So
yes,
they don't know
yes.
where to start to ask questions.
I'm sure they are enjoying a lot. So we can go
Okay.
and then at the end we can
Okay, I'll go ahead. So we have worked out the evolution of decoupling species in these two limiting regimes, ultra-relativistic and fully non-relativistic. But there are cases in which it is very important to follow more closely the evolution of these species with more refined tools, either because the decoupling is happening when the species are mildly non-relativistic, and therefore the expression that we have worked out before are not applicable anymore. Or because it is important to work out some quantities related to the decoupling of these species that cannot be retrieved with the approximated expressions. The tools that we need to follow the evolution of species out of equilibrium are given by the Boltzmann equation. The Boltzmann equation can be formally written in a very simple fashion in this way, where we have on the left the Liouville operator and on the right the collisional operator. The Liouville operator is basically telling how the distribution function or any other quantity that we can feed into the Liouville operator is changing as a function of the quantities on which the term inside the Liouville operator depends on. Basically, if the distribution function depends on time, on position, on momentum, on direction, whatever, the Liouville operator is taking into account the variation of the distribution function with respect to any of this quantity. In the Friedman-Robertson-Walker case, we have seen that, and in the homogeneous and expanding universe, we have seen that the distribution function is just a function of the of time and of the magnitude of the momentum of the particle, or the energy of the particle. And therefore, in Friedman-Robertson-Walker, the Liouville operator takes a very simple expression. The collisional operator takes into account all the different interactions that are causing the variation of the distribution function or of any other quantity related to the evolution of a given species. In case of no interactions, the collisional operator is very simple and simply equal to 0. Whereas in case of different interactions, we have to write down the expression, or rather lengthy and complicated expression of the collisional operator in terms of the different interactions that we want to account for in the Boltzmann equation. The bottom line of the Boltzmann equation is to tell us how the metric that enters into the expression of the Liouville operator here. We've seen here very clearly that the metric is defining the Liouville operator. So the Boltzmann equation is telling us how the metric affects the evolution of a given species depending on the interactions of this species with the rest of the other components. The Boltzmann equation is applied very usually in the context of the standard Big Bang model to some key epochs throughout the expansion of the universe, and these epochs are usually given by the Big Bang nucleosynthesis, or the epoch at which the relic density of dark matter sets in, so the freeze out of dark matter, or the recombination epochs. The description is very similar, so I will not follow all these three different epochs or situations during this lecture, but rather I will focus on recombination, since this will be important also for the remaining of our lectures, and it will be applied to the case of the cosmic microwave background. We can start from a very simple picture of recombination by using some approximate result in terms of equilibrium distribution. Recombination basically happens when all the ingredients for recombination, so electrons, protons, and hydrogen atoms, are non-relativistic. If we impose thermal and chemical equilibrium before the interactions that keep all these components in equilibrium start to be inefficient, charge neutrality, so basically the universe is neutral, and positive charges compensate negative charges. And finally, baryon number conservation. We can work out this expression here, which is the SA equation. And this is telling how the equilibrium distribution of the hydrogen atom can be written in terms of the temperature of the universe, the number density of the other species, and B, which is the binding energy of the hydrogen atom. If we introduce the fractional ionization, which is the ratio between the number density in electrons and the number density in baryons, just a quick note, in cosmology, when we refer to baryons, we refer both to baryons and also to leptons. So I'm considering in baryons any ordinary matter component. So if we define the fractional ionization and the baryon to photon ratio, which is the ratio between the number density in baryons and the number density in photons, the SA equation can be recasted in terms of the ionization fraction at equilibrium. And the evolution of the equilibrium ionization function as a function of redshift or the scale factor, which here is evolving in this way. So we are going from early times on the right to late times on the left. The evolution of the equilibrium ionization fraction is given in this plot, and so we start from 1, so the medium was fully ionized, until we start dropping down to very small values as the universe expands and the interaction that keeps the different components at equilibrium start to be efficient, and hydrogen starts to form, and therefore the number of free electrons start to decrease. The evolution is given for different values of the density parameter for baryons, because the density parameter enters here in terms of the baryon to photon ratio. Basically, the more baryons we have, the sooner the ionization fraction starts to decrease to 0. We can have a very rough estimate of the time at which recombination happens by finding some threshold value of the equilibrium distribution. Say, for example, that we define recombination to happen when the equilibrium distribution is around 0.1. So we draw an horizontal line here, and depending on the value of the density in baryons, we can find where this horizontal line encounters or intersect with one of these curves that represent the evolution of the ionization fraction, and this overlapping point corresponds to the redshift of recombination. If we insert the numbers that correspond to the observed quantities for the, for example, for the baryon to photon ratio, then we find that the epoch of reionization happens more or less at redshift 1100, which corresponds to a decoupling, to a recombination temperature of 0.3 electron volt, which has to be compared against the binding energy of the hydrogen atom, which is 13.6 electron volt. So naively, you would expect recombination to happen when the temperature drops below the binding energy. However, the fact that we have a very low value of the baryon to photon ratio, so we have many more energetic photons than baryons around, is responsible for the fact that it is important to arrive to very low temperature before the recombination can take place. This is the reason why the recombination temperature is so much lower than the binding energy for a hydrogen atom. Now, this picture is based on the fact that we are considering equilibrium distributions. And as you can see from this plot here, if we keep going towards late time and low redshift, the equilibrium ionization fraction is going to 0. However, this is not observationally the case because we observe today a non-zero fraction of free electrons. So recombination is not complete in a sense that it gives us a non-zero value of the ionization fraction even after the time of recombination. In order to find what is the relic value of the ionization fraction, and in order to fully characterize the physics of recombination, we need to use the Boltzmann equation for the ionization fraction or for the number density of electrons. If we plug in the correct expression for the Liouville operator and for the collisional operator in the case of recombination, we end up with this expression of the Boltzmann equation for the energy density of electrons, or this expression here if we consider instead of the number density of electron, the number of electrons. So n big N is small n times a to the cube. This expression, especially the one on the right of the Boltzmann equation, tells us something very important if we consider the two limiting cases in which the interaction rate gamma is much larger or much smaller than the expansion rate of the universe. When the interaction rate is much larger than the expansion rate, then the interactions are very efficient, and by inspection we can see that the solution of this equation in the case of gamma much larger than h is n equal to n equilibrium. Basically, the very efficient interactions force the number of electrons to follow the equilibrium distribution. And this is the regime in which the previous expressions in terms of the psi equation and the equilibrium ionization function are still valid. However, as the universe expands, we arrive at the time when the expansion rate dominates over the interaction rate. At this point, the interactions are inefficient, and the Boltzmann equation is telling us something different from the picture that we have seen before. The solution to the Boltzmann equation in the case of the expansion rate much larger than the interaction rate is telling us that big N is going to a constant value. And so that basically we are arriving at a residual ionization fraction due to the fact that at some point the interactions that we were considering before are not efficient anymore. This condition is pictured in this plot on the bottom, where you can see again the ionization fraction on the y-axis as a function of redshift. And in this case, we are going to small redshift here. So early times are on the left and late times are on the right. The dashed line represents the solution to the ionization fraction based on the Sa equation that we have seen before. So based on the equilibrium picture that we've seen before. And we see that we have almost completely ionized universe until a given epoch when we start to drop down due to the fact that we have dropped below the temperature for reionization. However, if we evolve the Boltzmann equation, we end up with a solution that is given by the solid line here. The solid line overlaps with the Sa equation, so with the equilibrium solution up to a given time. But when we arrive to the regime where the expansion rate is larger than the interaction rate, then the difference between the exact solution given by the Boltzmann equation and the equilibrium solution given by Sa start to diverge from each other. And the exact solution, instead of going to zero, goes to the residual ionization fraction, as we expect from astrophysical observations of the ionized medium. Any questions or comments so far? Okay, then we are almost at the end of the lecture. We have just 20 minutes to go, and probably we will not cover everything during this first lecture, but let's see where we arrive before I leave some time for discussion or questions. The discussion on recombination was intended to be as the last topic on the background evolution of the universe. So the evolution of a perfectly homogeneous and isotropic background. However, we know that the universe is not homogeneous and isotropic because we observe the large-scale structure of the universe, basically galaxies, galaxy clusters, and the huge web structures that you have seen in some pictures or in some videos of numerical simulations of the cosmic web. And we also observe anisotropies in the distribution of the cosmic microwave background temperature on the sphere. Before discussing where the seeds of these inhomogeneities and anisotropies come from, we would like to discuss the tools that we need to describe the evolution of the perturbed universe, similarly to what we have done for the evolution of the background homogeneous and isotropic universe. First of all, it is important to understand that as long as we can treat inhomogeneities and anisotropies to be very small compared to the background values of the quantities of interest, energy density, pressure, whatever quantity we would like to define. So as long as the inhomogeneities and anisotropies are small compared against these background quantities, we can be in the linear regime, and we can treat the evolution of these inhomogeneities and anisotropies in perturbation theory. Since we would like to focus on perturbation theory, we would like to perturb both the metric and the stress energy tensor and the distribution function that we will use to derive the integrated quantities over the momentum distribution. If we do so if we perturb metric, stress energy tensor, and distribution function, we end up with a set of Einstein equation for coupling the metric to the stress energy tensor and Boltzmann equation for describing the evolution of the distribution function, which can be rather complicated. However, as long as we are in linear theory, we can switch to Fourier space, So we move from the real space to the Fourier space, and this will come with two important results, or two important simplifications to our set of Einstein-Boltzmann equation. First of all, we can switch from a system of ordinary equation. Yes, from a system of ordinary derivative equation to a system of partial derivative, the other way around, sorry. We can move from a system of partial derivative equation to a more simple system of ordinary equation. And the other important thing is that as long as we remain in the linear regime, we can treat each different Fourier mode independently from the others. So the evolution of perturbations in the linear regime does not mix the different Fourier mode, and we can follow each of these Fourier mode as if it were an independent set of equations with respect to the others. The other important point that I'd like to make before moving to the description of the perturbed universe is that according to our inflationary paradigm, the perturbations that we are going to evolve were originated from random fluctuations in the primordial universe, and the mechanism that generated these quantum random fluctuations was such that the distribution of these fluctuations was Gaussian. The universe can therefore be considered as a result of a stochastic process, and as such, we are not interested to the individual or specific values of the perturbed quantities, but rather we are more interested into the statistical properties of this stochastic process. In order to characterize the statistics of the distribution of these perturbations, we need to know, in case of a Gaussian field, only the average of the distribution and the variance of the distribution. But since we are considering distribution of perturbations, it's simply to understand that we don't care about the average, because the average can be taken out, so it can be cast to zero. And the only important quantity that we would like to reconstruct after evolving the set of perturbed Einstein-Boltzmann equation is the variance of the distribution of such perturbations. This will be true both for the distribution of the density or matter perturbations and for the distribution of the CMB anisotropies. Basically, everything that we set up now and that we will discuss tomorrow in the second lecture is needed in order to characterize the so-called power spectra of the matter distribution of the universe and power spectra of the cosmic microwave background anisotropies. So after this introduction, let me just quickly introduce the perturbed universe for a few minutes before I leave time for questions and discussions. Let's start with perturbing the metric. You recall the Friedman-Robertson-Walker metric. It was given by this expression here, where we don't have the perturbation Hij. So the perturbation to the metric, this specific choice of coordinates, which is the so-called synchronous gauge, can be expressed in this way. So we are perturbing just the spatial part of the metric in this coordinate system. And this perturbation can be further split in different components: scalar, vector, and tensor perturbation. You have not to worry about these different components because we have a theorem, which is the decomposition theorem that we will not prove during this lecture, but can be proven in a very simple way, just some algebra. This theorem is telling us that the different kind of perturbations that we can apply to the metric, so scalar, vector, and tensor, decoupled from each other and can be treated independently from each other. So roughly speaking, this means that we can write down a set of equations for the evolution of scalar perturbation, another set of equations for the evolution of tensor perturbations, and we will not care about vector perturbations since they are negligible and they will decay very soon if they were present at all in the early universe. So we'll just focus on scalar and tensor perturbation, and the decomposition theorem is telling us that we can evolve the two sets of perturbations independently from each other. The other thing that we have to do is to perturb the distribution function. Remember that in the Friedman-Robertson-Walker metric, the distribution function just depends on time and energy. In this case, we can keep the equilibrium distribution function, but we have to introduce the perturbation that in principle can depend also on the spatial coordinates, but also on the direction of propagation for the different perturbations that we are going to consider. Of course, when we write down the Boltzmann equation, we have to take into account these new dependencies in the Liouville operator. Remember that the Liouville operator must know about any of these dependencies here, and therefore the Liouville operator for Boltzmann equation in a perturbed universe will take a slightly more complicated form than the Liouville operator that we have seen before. And also, we need to perturb, of course, the collisional operator if needed. If we do so if we introduce the perturbed expression of the distribution function, the perturbed expression of the Liouville operator up to first order, remember that we are in the linear regime, so let's just keep first order terms. We end up with this slightly more complicated expression of the Boltzmann equation for scalar perturbations, where here eta and h are the two components of the scalar perturbations to the metric. Epsilon is related to the energy of the species that we are considering. Q is related to the momentum of the species. And the Boltzmann equation is already written in Fourier space. This is the general form of the Boltzmann equation. What it is usually done is that this full expression is further expanded in harmonics, so is expanded over a basis that is composed by Legendre polynomial. And this is useful because the decomposition in Legendre polynomial allows us to disentangle the different momenta of the integrated distribution function. So the first order momentum will give us the evolution of the density perturbations. The second momentum will give us the evolution of the velocity perturbations, the third momentum, the anisotropic stress, and so forth with higher momenta. So it is useful to decompose this expression of the Boltzmann equation in the different momenta expansion in terms of Legendre polynomial, and to write down a Boltzmann equation for each of these momenta. Okay, let me just walk you very quickly through these two last slides and then I will stop. We have perturbed the Boltzmann equation you don't have to worry too much about the details. I just like you to understand what are the steps that need to be done when we have to evolve the perturbed universe. We have perturbed the metric. We have obtained a set of perturbed Boltzmann equations. What we need to do now is to obtain a set of perturbed Einstein equations. So the last thing that we need to do is to introduce perturbations in the stress energy tensor that are represented here as an example of the scalar perturbations. So you will recognize these additional terms, delta rho, Vi, and delta P and sigma ij, which are not present in the case of the background stress energy tensor. And inserting this expression of the perturbed stress energy tensor into the Einstein equation, we can work out the Einstein equations for the scalar perturbations to the metric in terms of the perturbed stress energy tensor. Here I reported an example of the Einstein equation in the Newtonian gauge, so using a different coordinate system with respect to the one that I used before, but this is just to show you that if we focus on the first Einstein equation and we neglect for a moment the expansion, so all the terms that depends on the scale factor, it is easy to understand that the first Einstein equation is nothing but the Poisson equation in terms of the perturbed quantities in the universe. And the second equation is instead telling us that the two perturbations to the metric are equal to each other if we don't have any anisotropic stress in the components of the universe. This is for scalar perturbations. Now let's quickly move to tensor perturbations. In the case of tensor perturbations, we still have two functions that we use to perturb the tensor part of the metric. And you might have seen already this expression multiple times, because this is the expression that is always related to gravitational waves, as you can imagine. So in the case of tensor perturbations, we express the perturbation to the metric in terms of this traceless and symmetric tensor. And repeating the same steps that we have seen above, so perturbing also the stress energy tensor, including in this case tensor perturbations, we can derive the Einstein equations for the evolution of tensor perturbations, which simplified in a case of vanishing tensor anisotropic stress. So there are no terms on the right hand side of this expression. And this equation here, you might have recognized it already, is the expression for the evolution of gravitative waves, of gravitational waves. So if there are tensor perturbations to the metric in the early universe, we expect the evolution of primordial gravitational waves. And indeed, this is one of the holy grails of standard cosmology. Try to observe the primordial gravitational waves that are linked to the tensor perturbations to the metric. And I will stop here and leave some time for questions and comments before moving to Gather Town, if there are people who want to discuss on a more offline basis. And sorry for taking so long.
Thank you very much, Martina. Thank you, thank you. So please, questions? Okay, we have one in the chat from Paul De Brayas. Sorry, Paul, I hope I have pronounced properly your surname. Would it be possible to post the slides on the Indico page? I think so, right? I mean,
yeah, it's fine. It's fine for me.
I mean, we are also recording. We are also recording the talk. So there are two questions now. One from let me see if I can see. Here, okay.
Hello,
Abiyat.
Arghajit Datta. Yeah.
Okay, go.
Okay. So, hi.
Okay, go
I
ahead,
have
please.
one or two silly question. It may be, I mean, related to mathematics, I think. So, while you showed the Liouville operator initially, in the, I think in slide 19 or 20 or somewhere there.
Okay.
So, no, no, no. Sorry, not 19. In 21, I think.
Ah, okay.
21, 22. Next one. Yeah. So
Yeah.
here for FLRW, we are getting like del f del t. I mean, in function in. I mean, it will be in terms of f. So next slide, while writing the Liouville operator for, let's say, electron. Next one.
Okay.
So you are writing in terms of number density in E
Yes.
dot plus. So how to transform that? I mean, simply doing the integration, or
Yes. Simply
there we
integrating
have.
over momenta. Yeah. Yeah, you write down the Boltzmann equation for the distribution function and you integrate over momenta and you get the expression for the number density.
Okay, so there we have like something like del f del E. So yeah, I mean I have to do that. Sorry. So that's one question I have. Okay, thank you.
Sure.
Julien Proste has a question, so please go ahead, Julien.
Yes, can you hear me?
Yes.
Okay,
Yes.
great. Thank you for the lecture. About this slide precisely, I had a little question. So we see on the Boltzmann equation that if gamma is really big over h, really, then n is forced to follow the equilibrium value. And on the contrary, if gamma is very small, then the derivative is also equal to 0. So, but when gamma is really high over h, do we have a precise mathematical argument that says that we have to follow an equilibrium, or is it just like we sort of feel it has to be like that?
No, I mean from the mathematical point of view, it follows from the exact solution to the Boltzmann equation. So you work out the solution to this differential equation, and you see that there is a regime at very early times where n is going like an equilibrium, and indeed this is also shown by the plot at the bottom, where at very high redshift you have that the solid line is basically following the equilibrium solution that is given by the psi equation. The solid line is the exact solution to the Boltzmann equation. It's not an approximation or a qualitative approximation. It's the solution, the mathematical solution that you obtain for the Boltzmann equation. So yes, if you write down the formal solution, you see that at very early times or very high redshift or small scale factor, n is following the equilibrium distribution, what you would expect from an equilibrium distribution solution.
Okay, thank you.
Sure.
I have another question from Pablo Martinez Mirabe. Pablo, please unmute yourself and go ahead, please.
Hi, thank you, Martina, for the nice lecture. So regarding what you said on perturbations, vector perturbations, is there an easy reason to understand or physical reason to understand why do they decay?
The vector perturbations, you mean?
Yeah.
It's again, I mean, from a formal point of view, you can work it out by following the same steps that I highlighted for scalar and tensor. You write down the Einstein equations for vector perturbations once you perturb both the metric and if needed the stress energy tensor, and when you work out the solution, you see that even if they are present at early times, their solution indicates that they quickly decay as a function of time. So from a more qualitative point of view, I have to think a little bit more. I don't have an answer on the top of my head, but it follows simply from the formal solution to the equations. I will have a look and let you know either tomorrow or today if you are on Gather Town. Sorry.
Sure, thank you very much.
Okay, are there any more questions for Martina? More questions? Okay, not. Thank you very much, Martina. Let's thank all of us for this wonderful first lecture. We are eager to listen to you tomorrow, to the second one, Martina. So I'll see you tomorrow. I will see you tomorrow, and all of us, of course, at 12, right?